Something's happening.
Right. Phew. Okay. So we've got a bunch of invariants and a bunch of 4 vectors. So one of the 4 vectors we've got is the position. This one. The next one is the velocity. And that's the differentiation of this vector with respect to not time, not to t, but to the time associated with the particle itself. Okay, so that's the tick marks, not on here, because that would just give me the value c, but on here, which is normally called tau or proper time. Okay, if I differentiate t with respect to tau, that gives me the gamma, which is the gamma that you see out in front here. Okay, so that's the 4 velocity. Then you have the fact that the 4 velocity has this invariance. Now this dot here, that was on the previous slide. To get the dot, you just you take V transpose G V, which is V dot V, where this G is this matrix -1, 1, 1, 1, and zeros everywhere else. In other words, we take that squared. I keep doing it the wrong way around. Sorry, there's 2 conventions. I should use plus, minus, minus, minus. So it's that squared minus v squared. Okay, c squared minus v squared times gamma squared. Okay, and that gives you c squared. So v dot v is c squared. And then the momentum, if you multiply this vector here, this 4 vector, by m, by the rest mass, m0, you get this quantity here. And this is the 4 momentum. Okay, that consists of 2 bits, a single piece here, which is m0 gamma c. Okay, and we associate that with the energy of the particle. Okay, so the 4 momentum is sometimes called the energy momentum vector. Okay, and then m0 gamma v is the relativistic momentum. Okay, now some people call m0 gamma, they call it the relativistic mass. I'm not keen on that, but you will see that in the literature. Likewise, m0 gamma v is a relativistic 3 momentum. Now, what's useful? And then there's the force law, which tells me that the rate of change of the relativistic momentum with respect to tau, that's the proper time, okay, is proportional to the force. So this is the generalization of Newton's law, okay, and that picks out an extra gamma in front because you have this dt by d tau, and dt by d tau is gamma. So if we take the 3-force equation, okay, we have dp by dt. Okay, and that gives me d by dt of gamma v. So if I want to increase my momentum, okay, if I'm at low velocities, if I keep applying a constant force to, say, my electron, okay, then initially gamma will stay very close to 1, and everything will change in v. Okay, so if you're dealing with a klystron, or you're dealing with the old cyclotrons, the low energy machines, then it's mainly v that you'll be dealing with. But as soon as you get to relativistic velocities, especially with an electron, which happens pretty quickly, v stays pretty constant because it can't go any faster than the speed of light. And so all you're doing, all in quotes, you're doing is changing gamma. Okay? So you just keep adding energy to the particle. Okay, you've got this momentum invariant here. So P dot P, remember P, that's the M naught gamma, oh god, I can't remember the C's. So P is this one. Yeah, M naught gamma C, and then gamma V, M gamma V, M naught gamma V. Okay, so there's my P. If I do P dot P, I've got that squared minus that squared. That's going to give me M naught squared C squared. And of course, Einstein told us that E equals MC squared. So this actually is just the rest mass of the particle. And that doesn't change. That's an invariant, which is what you would expect. You wouldn't expect that the rest mass of the particle, even the name rest mass, the mass that it measures at rest, is not going to change if you move it, because it's a name, so it's the rest mass. If I differentiate that with respect to tau here, okay, so if I differentiate a constant, I'm just going to get 0. This is just M naught times V, so that gives me V dot dp by d tau. Dp by d tau is the force. Okay, so that tells me that the ball velocity is perpendicular in a 4 matrix then to the force, and the ball velocity is perpendicular to the acceleration. So if we multiply that all out, we get that this the rate of change in the energy. Remember, this is M naught gamma. So the rate of change of the energy is V dot F. Well, we know that because V dot F is the work done on the system. So that's just your Newton's equation in the 4 velocity case. So the rate of change, V dot F, is the rate of change for work was done. It's the rate of change for kinetic energy. Therefore, the kinetic energy is M. MC squared. This M here, of course, is M naught gamma, which is why it's equal to that. Okay. And that's why you can associate M naught C squared with the rest mass of the particle. Right. So here's a summary of the 4 vectors that you're likely to deal with: position, velocity. So it's 4 position, or an event, 4 position, 4 velocity, 4 momentum, and 4 force. I don't think I've ever heard it called 4 force, but there you go. Okay. Oh yes. Right. So here's a nice thought. So we're used to Galilean transformations. We're used to, you remember ships that pass in the night. Did you do these calculations at GCSE? You have one ship going in that direction and another ship going in that direction. How close do they get to each other? And what you do is you add the vector, one vector to the other vector, so that you can think of one of the ships being at rest and the other one just going past it. And then it's easy to work out the closest distance. So essentially you just add the 2 vectors. Now, if I'm, yeah, so, right, I'm going to need a victim here. Here you go.
Did you point it there?
Hey?
Did you point it
Yeah.
there?
So you move quite slowly past in that direction.
This way?
Yeah. And then I move faster than So I'm moving at twice her speed. So she's moving at 1 unit per second, and I'm moving at 2 units per second, and she would observe me as moving at 1 unit per second. So you just add them together. Thank you.
Thanks.
But if she were moving at half the speed of light, or let's say 3/4 of the speed of light, and we just add her velocity to my velocity, and I'm moving relative to her at 3/4 of the speed of light, it would mean that I was moving relative to the whiteboard at 1.5 times the speed of light, and we know that you can't move faster than the speed of light. So we know that something's going to happen, something that adding velocities, you can't just add the two velocities. So what you have to do is, well, the easiest way is to do these, well, one method is to do the Lorentz transformations. Okay, so now Chris has decided that he's not just going to add two velocities both moving in the same direction. He's going to add one velocity v, which is moving parallel to the x coordinate, with another velocity u, which is moving at an angle. Okay, so this is a more general case. Okay, so he says an object has velocity u in frame f prime, so that's in the moving frame, which moves at velocity v 0 with respect to frame f. So we've got three things going on here. We've got a frame at rest, so that's my f frame. We've got a frame that's my f prime frame, and then I've got this thing here. Okay, so this is moving relative to this, and this is moving relative to this. How does this relate to this? Okay, and clearly, no matter how fast I go, I'm never going to move faster than the speed of light. Okay, so I have to map, what do I have to do? I have to map the F. So he's going to map the U frame here. He's going to map this velocity onto here. Okay, so we use the Lorentz transformation matrix here. This vector here, okay, that is this vector. Okay, that's the three-dimensional version, or two-dimensional version. Okay, so we have to multiply by gamma, okay, and that gives us the 3 vector associated with that. It should really be a force vector, but we're ignoring that bit down there. We multiply everything out. That move, this is going to map us now into the W frame. So this is going to be what is we know what this is in relation to this. Now we're going to work out what this is in relation to that. I've just realised that blue line. Oh no, that's right. That blue line is right. All that. Okay, so we do the multiplication. It's a matrix multiplication, bit of manipulation, and you end up with this is what the W looks like. That's standard just basic manipulation. Okay, and that tells us how to add the vectors, and you see that I've got this sort of suppression bit down here. Okay, if I set uy equal to 0, then we can just ignore that bit. Okay, and we've just got this thing going on here, and it doesn't matter how close to the speed of light this is. If both of these were very, very close to the speed of light, okay, we'd end up with sort of 2c upstairs, but we would be dividing by, well, this thing here would almost be c squared, 1 plus c squared. That gives you, so 1 plus 1, that's 2. So we've got 2 divided by 2. It's going to give us 1 again. So we add two things that are very close to the speed of light. We just get another thing that's very close to the speed of light. And then obviously if we're in higher dimensions, we've got a more complicated formula. But an easier way of doing it is looking at these invariants. And the point about where I have a dot here is I'm going to have an invariant, and they're much more useful. Okay, so you evaluate what u and v are in the f prime frame, and that tells me that u dot v, which is that squared minus that squared minus that squared, which gives me this value here, that is an invariant. Okay, which means it's the same in every frame. And then I can work out what it is in the other frame. Okay, and just a little bit of maths without having to work out all these what's relative to what and drawing pictures is you can just get the answer that will fall out quite quickly. Okay, so using these invariants really becomes a powerful technique. I think we've pretty much covered all of these. It turns out people got very bored with dividing by c all the time, and they took two different approaches. The mathematicians just said, well, let's work in units of 1 second and 1 light second, so c is 1, so I'm just going to ignore it on my equations completely. But the engineers and the physicists thought, no, I'm going to just change my v into a beta, so my beta just is v over c. Okay, that's it. I like this one. Okay, this diagram here is particularly useful if you're doing acceleration and you're working at the TeV scale. Okay, so here here's my TeVs. Okay, and this is my Newtonian velocity. So this is what I would observe in my lab frame, the speed at which it's moving. Okay, now protons classically, they would do that. Okay, if I were purely Newtonian mechanics and I kept adding energy to my protons, if my protons got 250 TeV, that's a half mv squared. 700 TeV would be up there, it'd be faster than the speed of light. Okay, so we know that's not right. Okay, well, this is what protons in reality do, or due to special relativity, and you see that it approaches the speed of light, but never quite gets there. Electrons, well, electrons are much lighter, so in this scale, we almost, well, we get, you're at the speed of light almost instantly. A nice question is, what is this curve, the green curve? I say curve. Is it what it looks like on there? Nobody wants to volunteer an answer. Any ideas?
It would be the same as the proton.
It is in fact the same as the proton one, just squashed down by a factor of 1,000. Was it 1,000? No, 2,000, isn't it? So if you take this red line and you squash the scale by a factor of 1,000, you'd end up with a green line. Okay, that's all that's going on. It's just that because electrons are so light, by the time you get to TeV, they're virtually going at the speed of light. I thought protons, if you get to TeV, they're virtually going at the speed of light. So that's what we worked out. Oh well. Oh no, that's a TeV. Is that? That's a TeV. Okay. This is actually MEV. Yes, that makes sense. Phew. Oh, it's TeV. Yes, I thought it was not TeV. Okay, so if you were to draw the same sort of scale related to the LHC, for example, where so this is at rest and this were 7 TeV, then that would be the shape of your proton. But at low energies, as we said before, you see these two here are very, very close So at low energies, you might as well use Newtonian mechanics. And it starts becoming relative. Well, we talk about the things being relativistic. If you need to put relativistic corrections in, typically you need to put relativistic corrections if it's more than 1 or 2%, maybe 10%. So you need to be at least, 20% of the speed of light before you need to start worrying about relativistic corrections. Okay. Some important invariants. Okay, well, P dot P, as I say, whenever you see a dot there, which means the first object squared minus the square of all the other objects in a vector, that's an invariant, which means it's the same in all frames. Okay, and so P dot P, that's E squared over C squared minus P squared. Do you remember? A P here, you can barely read it. That thing, M naught gamma C, that was our energy. Is that energy? I'd have to work out the units as to whether, I think that's energy over C. M naught gamma V, that's the little p here. So if I take the square, P dot P, I end up with this quantity here. And that relates the scalar momentum to the energy, okay, which is useful to have. There are some basic manipulation. If I take, how have I done here? What's he done over here? It's multiplied by the c squared. He's taken that over to that side, taken that over to that side, so we've got a difference of squares, E naught being the rest energy, okay, and then basic manipulation. So if we talk about the energy of the particle, remember when we talk about the energy, especially of protons, we have to the total relativistic energy is the energy of the beam plus the rest energy. So if we talk about a 1 GeV proton beam, then that is, if you like, the kinetic energy. That's your so we've got the total energy. That is the energy, that's a kinetic energy, plus the rest energy, i.e. m naught c squared. And this thing is a, I don't know, we call it EK or something. So the total energy is the kinetic energy plus the m naught c squared. So if I if I talk about a proton beam of 1 GeV, you've got to add to that the the rest energy, which is also 1 GeV. So the total energy is 2 GeV, okay, which means that my gamma, so this is gamma m naught, gamma m naught, my gamma is equal to 2 in this case. So for a 1 GeV proton beam, my gamma is equal to 2. So if I have, well, this is practically what this is to say, okay, and that's giving me my proton energy. Oh yeah, and then I can work out from my gamma. So in this case, I've got more accurate figures, okay, and that's going to give me my gamma near 2, which gives me my beta of values just slightly quite close to the speed of light. Okay, if I'm worrying about slightly changing the energy of a particle. Now, it often happens, especially if you're doing things like beam dynamics, that you're not interested in what the absolute velocity is, because almost all particles are traveling around the ring at almost the same speed. Okay, what you need to know is what's the relative velocity between something moving at the front of the bunch and something moving at the end of the bunch, or something slightly off the ideal orbit. Have you done? You're going to be doing lots of work on transverse beam dynamics and longitudinal beam dynamics, and this is all asking questions about not what does the whole bunch do. The whole bunch just shoots round at the design velocity or the design energy, but what the bits that aren't quite in the right place are doing. Okay, so these are small parameters compared to the big parameter for the thing going round. Okay, and this is why you need to know a bunch of equations for changes in these, and this is just like perturbation theory. You start with your equations, you differentiate them. So if I take this, gamma beta squared is gamma squared minus 1. That's just your v dot v equal to c squared equation. Okay, and then I differentiate it. So I use a delta symbol, manipulate that a bit, and I get this relationship here. You can do that with all your equations. Okay, and so what's the relationship between, if I want to make a small change in beta, and let's say I'm very close to the speed of light, okay, I need to make a big change in gamma, which is what you would expect. If I'm very close to the speed of light, okay, and to go from 99.9% of the speed of light to 99.91% of the speed of light, that's quite a jump in energy. Okay, and that's what this is saying. So these are your sort of first order equations. So valid for first order only. There's a little exercise there. I don't know when you're given the exercise. Do you have a tutorial with this lecture course? Probably. There they all are. I'm not going to go through. Well, there are some of them. Some relationships. So small changes. I guess the most useful one is probably these sorts of things, small changes in energy, how they related to small changes in beta, or small changes in gamma, and so on. But these are the fun ones. Okay, so now we're going to get more into the particle physics. So let's pretend that we've designed the most brilliant particle accelerator. We're actually going to use it to collide things together. I think we kind of forget about it then, don't we? We've done our job. We've produced the beams. But there are lots of calculations to do with colliding things together. And by looking at these invariants, you can do a lot of things, make life a lot easier than trying to do Lorentz transformations, which are quite nasty. Okay, and we tend to use momentum, the full momentum, a lot. Okay, and we know that if we have things colliding, okay, then, and we look at what happens before and after, we know that we have conservation of energy and conservation of momentum. But in special relativity, okay, you end up with conservation of the full momentum. Okay, so this is the only equation you have to remember. This and the fact that if you dot two things together, you end up with an invariant. You pretty much do most of the questions just with that information. So remember, this big P here, that is consists of two bits, the energy and the momentum. Okay, and the total for momentum is conserved. Okay, so here's a classic problem. Given a mass which starts off at rest, and let's say it disintegrates spontaneously into two masses, okay? Those two masses, they're different, M1 and M2. They fly apart from each other, so there's some leftover energy, gives them converted into kinetic energy. Show that the kinetic energies of these are given by these two formulae. Well, we can get away. We have a single particle before that has this 4 vector, so it's at rest, which means that this bit is 0, but it has a rest mass, big M, so we've got big MC for this, for its energy. Afterwards, well, the relativistic energy, so remember this includes the rest mass. We've got E1 over C and P here. Now, whatever my P must be, because I have conservation, okay, I know that P equals P1 plus P2. Okay, because that's equal to 0, then these two must be equal and opposite. Okay, and then I've got a relativistic energy here and another relativistic energy here. Okay. Okay, so conservation of 4 momentum, that tells me that P4 is equal to P1 plus P2 afterwards. Okay, now, because Chris is very good at doing these sorts of equations, he spotted a particularly quick way of doing it, which you might not get the first time, where he says, well, instead of doing taking that dotted with itself and that dotted with itself, instead he's taken the P minus P1 and he said, well, that must be equal to P2. That's easy enough, taking that over to the other side, and that must be conserved. So that's going to give me, so if I dot it now with itself, so I've got P2 dot P2, well, P2, that's this relationship here, what is that equal to P? He's done a few steps here. I can't see what he's done here. I did work this out, but it seems all a bit mad now. Right, so I've got P dot P, so I've got that bit, I've got that bit, I've got that bit, so I can see where this is coming from. P dot P, that certainly is, oh, I know what's going on, sorry. P dot P, that's M squared C squared, you can see that from here. P1 dot P1, okay, he's defined M1 squared, that's just his E1 squared with some factors of C floating around, okay? So that's your, the relativistic mass associated with M1. This is the relativistic mass associated with M2. And then we have this quantity here, P dot P1. Well, P is this and P1 is that. Well, this bit here, that's going to give me 0. So all I'm left with is MC times E1 over C, which gives me this quantity here. And so if I just simplify everything, get E1 to be the subject of the equation, I get this equation here. I think I'll just M0 here, that's the rest mass of the initial one, but the M1 and the M2, that's the relativistic mass. So they're the ones with the gammas in. Okay, so it's not obvious without actually going through the calculation, when you write down an m, which m you're talking about. Okay, but particle physicists do tend to talk about the relativistic mass a lot more. Here's another example. Okay, two particles have equal rest mass. Okay, in frame one particle is at rest, the other has energy E1. In frame two, in the center of mass frame where the velocities are equal and opposite, the total energy is E2. Okay, the problem is to relate E1 to E2. Okay, well in E1, the total energy, well, one of the particles is at rest. That's just going to have that's its rest mass. It's going to have zero momentum, so that's what the vector is. Okay. In frame two, sorry, in frame one, there's P1. Okay. The total energy is E1, so that's the total relativistic energy. That's this energy. That plus that. Okay. That's why I have to subtract it off. Okay. So that gives me in that frame. Here they have equal and opposite momenta. Okay, and so there's my P1 and P2 in the other frame. Now, just by constructing this particular invariant, okay, by adding them two together and dotting it with P2, why P2? Well, P2 is the one that's 0 in here. Okay, so if you were to just see this problem, you wouldn't dream of coming up with this as being the solution, but this is the clever solution you get after playing around with these sorts of things for a long time. So you realize that this is an invariant here, so it's got a dot there, which means it's the same in both frames. Okay, so P1 plus P2 in this frame, you can work out what it is. It's going to be P1 plus P2, that's equal to E1 over C, comma T. But in the bottom frame, writing with a prime, I should really have P2 prime, that's in the second frame, that's E2 over C, 0. Okay, so they're my two, this side, okay, and I'm going to dot that with P2, okay, which is quite nice to have a 0 here, so I don't have to worry what's going on down here, and then I end up with, well, I've got E1 times M0, so that's this term, that's 0 times there, so that's that one, is equal to E2 over C times where are we? Yeah, E2 over C times yeah, then I have to use P2 in this frame, gives me that. Okay, so that gives me that quantity plus 0, and then a bit of manipulation gives me that relation. So by using invariants, you can see you get to the equation much quicker, the answer much quicker. I should say using invariants. And using invariants in about 10 or 20 years of intuition means that you get to the answer much quicker. Because I'd have never dreamt of doing them this way. Okay. So what's the relevance of this? Well, in particle accelerators, there's usually two different ways. You can either collide things together, which is the usual way of doing things, or you can have a fixed target and smash the other into a fixed target. They've both got advantages, but you'll see here that the advantage of using equal and opposite beams is quite significant. So in experiment 1, P1 and P2 have equal and opposite velocities in the lab frame, whereas in experiment 2 they have one's at rest and the other comes in and hits it. What's the relationship between the energies that you need if you want to produce two W particles where the the rest mass of a double W particle is about 100 times the rest mass of the proton. So you're firing, in one you're firing a proton into a fixed target to produce W particles. The other one you're firing two protons together. And you'd think, well, you only need a bit more energy, twice as much energy, 3 times as much energy. Well, maybe that's not what you think. But okay, so here's experiment 1. They're firing together, and they have the same rest mass. So how much energy do you need? Okay. So the total 3 momentum is 0 before, so it's 0 afterwards. The 4 momentum before, so that's equal and opposite energies. Okay. The 4 momentum after must still be equal and opposite with the 4 momenta bit. Okay. E, where are we? Total energy is conserved, so that plus that must equal that plus that, and which tells me that my E prime must at least be as big as my E, which tells me that I need energies of 100 m0 c squared, so I need 100 GeV, or 250 GeV beams. You know, two 100 GeV beams, and that you can do in a particle accelerator quite easily. Now, let's have a look what happens if you're hitting a fixed target. Okay. Well, okay, we've already shown, so we showed this before, go up. Yes. Here we can use this relationship. So this is a relationship between the fixed target experiment, E1, and the colliding experiment, E2. I think that's the right way around. Total energy, yeah, E2, two things are hitting each other, E1, one of them's at rest. Okay, so we've got this relationship here, and you bang in the numbers, and it turns out that you need a 20,000 TeV beam to do that. Yeah. So if you wanted to produce 2 W particles using a proton, using a fixed target, it's just inconceivable. Okay, so so that's why they don't. Okay, it's not 1 or 2; it's massive. What are the advantages for using a fixed target? There are a couple of advantages. They do use them for relatively low energy. I was thinking of something. Am I going to have to point at people?
All of the products will go in one direction.
Yeah, all of the products will head off in one direction. That's probably the main one. So they're easy to. If I'm colliding two things together, everything sort of hangs around the center. Okay, so unless I've got given enough energy that they're going to fly apart into the detection, I don't know where they are. Well, they're just going to decay where they are. I mean, but if I actually want to use the result of the collision for something else, okay, say I want to produce muons, which aren't quite at this energy, fortunately, then I would use a fixed target, because then my muons will all be flying out behind. Also, fixed targets are cheap. You're only producing one beam. Okay. So they are. We do use fixed targets, but we don't use them for producing W and Z particles, because it's just inconceivable. Okay. Light also has a 4 momentum associated with it. Okay, and the 4 momentum associated with light is given by its frequency and its k vector. So this is not so much 4 momentum, but the 4 vector associated with light. And you see, if I were to dot this with itself, okay, I would end up with omega squared over c squared minus k squared. But k squared is equal to omega squared minus c squared. So this thing dotted with itself is 0. So the 4 velocity of light has total length 0, and that corresponds to the fact that it's going, if you remember my space-time diagram, it's going along this 0 curve, okay? So the rest mass of even though it's got momentum and it's got velocity, well, even though it's got momentum, it's got no rest mass. The rest mass, remember, the rest mass squared is p dot p. Well, p dot p here is 0, okay? So the only way you can get something to move at the speed of light is if its rest mass is 0. And of course, as soon as its rest mass is 0, it has to travel at the speed of light, otherwise it doesn't exist. So things can either travel at the speed of light or not. Okay? Although that's true, there does turn out to be sort of a mathematical technique, a useful mathematical technique, where you can consider things traveling almost at the speed of light. So if you know of anything that spends most of its life traveling almost at the speed of light, then you can use sort of perturbation theory around the speed of light as a technique. Okay, and that's another way of handling of doing beam dynamics, where you actually do something as a perturbation around things going at the speed of light. It's quite an interesting perturbation, and we did that. You can look up some papers of mine where we've considered these things. So, but light definitely does move at the speed of light, but we still have some invariants. Okay, we have the position vector, the wave vector, so we end up with this quantity here. Okay, and that's the phase. So the phase of the light at a particular position is independent of what frame that you measure it in. Probably the more useful is the energy, the momentum. Okay, and that's given by this relationship where h bar suddenly comes in. This is the momentum of a photon. If you want to think of, you can think of light either as a collection of photons, which is very useful if you're doing particle physics, because you fire into protons, you get photons, genuine individual photons out, 2 photons that come out. They start interacting with other matter and start decaying. They don't really decay, but if they see some other matter, then they're going to interact with it. And that way you would handle it, and you'd have to have h bar in your equation, because a photon is a quantum mechanical object. But it's still useful to talk about the full momentum of light, even in even for classical electromagnetic radiation. If, say, you're firing it into a plasma or something like that, then it's useful to talk about those sorts of things. How long have I got? 1 minute. Okay, but I did start light, so I'm going to keep you over for about 5 minutes. So I'm going to whiz through these last slides. Relativistic Doppler effect. Okay, that's so you're familiar with the standard Doppler effect. That's light. You know, the standard joke. There's 2 ways of approaching a red traffic light. No, you either slow down and stop, which is the standard way, or you drive really, really quickly so that the red light appears to you as green. Okay, and then you can go through it. So that's your Doppler effect. It squashes light up. There's a weird one that if you consider, so you expect light. If you're running towards an object, then the Doppler increases the wavelength of light. If you're running away from it, it decreases the wavelength of light. But if you're running past it, it still decreases the wavelength of light. You get a second order effect, and that's purely relativistic. Okay, that wouldn't be predicted by standard things. So we've got there's even a transverse Doppler effect when you're running past something. Right. Okay. So the 4 acceleration. That's just the differential. I think we've seen the 4 force. We've seen that the rate of change of the 4 momentum is the 4 acceleration, is the 4 force. Okay, and the 4 force, the rate of change of the 4 momentum is just m times the 4 acceleration. Oh, standard all your standard Newtonian stuff that was a 4 put in front of everything. Okay, if you calculate it, so it's dV by d tau. Okay, that's the rest. That's the proper time. So you pick up lots of factors of gamma floating around, and because you've got an extra gamma floating around there, then when you convert everything into Newtonian to the Newtonian velocity, you pick up gamma cubes and gamma to the 4 floating around. Okay, so if you wanted to know, if you've got an a squared, okay, remember a dot a, that's an invariant. That is what the acceleration you would feel if you were sitting on the particle itself, okay, and you can work that out, and that then has a gamma to the 6. You're getting quite high factors of gamma. It turns out that the Larmor formula, so that's the energy that you get out from a particle, okay, that goes as a dot a. Okay, so the total energy that you get out goes as gamma to the 6. Okay, and then you can ask the question, well, where does that energy come from? And that's our discussion before. So if you're in the direction of motion, you have a gamma to the 6, but if you're perpendicular, it's only gamma to the 4. That's okay. So, yeah, and then you put that into other formulae that says that if you accelerate using an electric field, you end up with gamma cubed, but if you accelerate using a magnetic field, so if you accelerate in the direction of motion, it only goes as gamma cubed, but if you accelerate in perpendicular to the motion, it goes as gamma to the 4. So you get a lot of energy out when you start putting dipoles in the way, okay, which is why, of course, the LHC is so big, because this energy here, that's the energy you're losing that you have to put back into your proton beam. Okay, gamma is pretty high for in the LHC, and so you need to put in a lot of energy. You want as small as possible acceleration. Okay, well, that acceleration is the amount that you bend it. So you don't want a nice small. If you had an LHC that was the size of this room, okay, you would need an astronomical quantity of energy, a really strong field to keep them bending round sharply. So not only would you need really high fields, but what would happen is that it would that would produce vast quantities of synchrotron energy, which would kill everybody. So there you go. But would require, several plants you need a lot of energy to put back in to compensate for that. Uniform acceleration, there's some nice equations you can deal with that. Okay, one nice way of handling uniform acceleration is to use hyperbolic functions. Okay, and so on and so forth. And then I'm just going to spend a moment talking about faster than light motion. Okay, how do you create things that travel faster than light? Of course, nothing can travel faster than light, but if I have a very large pair of scissors, okay, then I can make the cross of those scissors, this point here, move faster than light. Okay, am I breaking relativity? Well, no information is contained in that cross. Okay, and what's more, the direction this cross is moving will be different in different frames. Okay, there'll be a frame in which this whole cross appears simultaneously at the same time. What's happening? Well, you're changing these angles. In one frame, they look like that. In another frame, they look like that. And in another frame, they look like that. Okay, not breaking anything. No causality is changing. I don't know this one, but the other one I do know. If I have, oh yeah, this is a weird one. It looks like if you look at a supernova, it sometimes can look like it's travelling out faster than the speed of light. It isn't. It's the effect of the way that light's travelling towards you. You know, that's just astronomical experiments. Anyway, hereby endeth the lesson. He's got something to do with it, and thank you very much. I hope at least sparked your interest. Good. I need a drink. Bye bye. No, I'll wait for that. Bye bye.
It says that in the emails. It's not here. No. Here, yeah. It says it was going to be in here. But he's not.
So just for the people who are watching, at the end I'm going to run through these slides again. Hopefully this will work. No, well, who knows what it's doing now.
You're not supposed to leave it?
It's not going to work anymore.
Just for the PhD students. What are you? Are you something else?
Yeah, like placement student.
Oh, placement students don't have to stay.
Press content. Oh well. You want that?
There's not really enough students here. Considering it's compulsory, we have more than 5 students in Cockcroft, and he's not even a student. I'll send an email round.
To run get biscuits and a cup of coffee.
Want to go before I say again?
What the hell?
Down somewhere.
It's here.
There you go. Oh God, I don't think I've plugged that in either. The poor people who've been watching.
It's alright, there's mics in the room as well.
Are you trying to happen everyone?
What's going on here? Something
Press the
weird.
top.
All right,
Press
the coffee.
Yeah, that's
I'll just be a
I'm wondering if I should
second.
do 6 coffees for the entire day, but
Is it coming up?
hang on.
Looks not.
Not eating biscuit. This own body of mine.
I'll plug into different number maybe? What number's this? This is number 1.
Right, I'm going to run away. Pretend that I don't know anybody.
There we go. Right, so,
We're just waiting for Victoria.
I'm back.
Isn't it?
Yep.
there we go. So, this is just an introduction for new PhD students to the Cockcroft Accelerator programme, and I'll better make myself up. And tell you what's expected of you, what's going to happen, etc. I'm the head of education and training at the Cockcroft. My name's Graham Barton at Lancaster University. If you have any questions about it, you can email me or find me about the Cockcroft at some point. So, our education scheme has 2 levels. We have introductory and we have advanced. The introductory lectures are for the first years only. Second years can attend if they want, but they're aimed at the first years. First years have to attend them. It's compulsory. And they run October to Christmas. And they cover the basics of the very basics of accelerator science, covering magnets, RF, accelerator science, and introductions to everything. Then we run the advanced course. Now, it's compulsory that all first and second years attend the advanced courses. So when you reach second year and in your first year, you have to attend all the advanced lectures. It is taken as a sign-up sheet out the back, and it's passed on to your supervisor. We have no lectures in July or August. apart from holidays, but we run all year apart from that. And the syllabus can be found on the Cockcroft website. If you go to Cockcroft Education, you'll find the syllabus for the current term. So this is the syllabus for this year. So introductory, this is the poster that's on the website now, and we have Introduction to Accelerator, which you've seen, Relativity you've seen. Next week we have Electromagnetism, and then we have Transversal Longitudinal Dynamics by Dr. Rob Appleby. Professor Neil Marks is doing magnets, and then I'm doing RF just before Christmas. There's tutorials for these three last classes, the dynamics, the magnets, and the RF, because those are examen classes, so there's tutorials for them. If you can't attend a lecture for some reason, you're ill or you're at a conference, we webcast them, so you can watch it live or you can watch on demand. They come up about 1 to 2 weeks after the lecture's taken place on the on-demand service, but live, we stream it live. So right now there may be someone sitting at Lancaster, Manchester, Liverpool watching this right now. Hello. You can also find the slides either, and loads of students can't find this, which I think is an IQ test. There's a wee button here that says files. If you click on that, it shows you the slides. Loads of students miss it and email me about it, but it's not that hard to find. Also, temporarily, we're going to start hosting them on a wiki space. That will be linked from the Cockcroft website as well. We've had problems, we can't upload the lectures to the website itself, so we've got a wiki space to last us in the short term. We're transitioning to a new website soon, and that'll have the lectures on it instead, but for now it's going to be on this wiki page. So, the course is assessed. You'll get your assessments in January, because we're not evil enough to give you them over Christmas. They are take-home assessments. They will involve you reading through the notes, understanding the notes, and a wee bit of additional research. The completion date for them is the 20th of March, and you'll be handing them out in January. The tutorials will be in December, but there may be some additional tutorials sometime between January and March. We haven't planned that yet. You will submit your coursework to Liz Kennedy, who's up on the top floor next to the director's office. And the coursework, you'll have 3 pieces of coursework to do, one on beam dynamics, one on magnets, one on RF. And it's compulsory that all students do all 3. Marks will be given to your supervisor, and your supervisor can do what they like with it, but we encourage that they use the mark as part of your upgrade review. All students have to pass first year, otherwise they get kicked out of the course. It's not just PhDs are 3 years and then at the end, you pass or fail. There's transition points where you get to decide if you get to continue or not, and some students are asked to leave the university at the end of the first year. So each university is different, but at least at Lancaster, we will use this information as part of the decision whether you continue on to the next year or not. We also run a postgraduate conference. This is for all students. You as first years will come to it this year, but you won't present. It usually happens in October each year. This year it's running a bit late. The guy organising it's been off sick. So sometime in October or November we'll have this conference. Every PhD student in Cockcroft that we can persuade to present will present, and there's a prize. The prize is usually money, Amazon vouchers, something like that. They usually give one for each year group, so one for first years, one for second years, one for third years. So you won't present this year, but you'll expect to come and view the presentations, so you get an idea about what a second year student should be doing, what a third year student should be doing, an idea about what's going on in Cockcroft. And these are some previous winners here. Interestingly, we had one from Manchester, one from Lancaster, one from Liverpool, but that was coincidence. We don't deliberately do it that way. For each course, we expect you to fill in a feedback form to allow us to improve the lectures for future years, and maybe even improve the lectures for this year if the lecturer is giving 2 courses. It's a very simple form. 6 questions, you rate 1 to 5, plus some boxes to give us additional feedback on how the course could be improved. It's very important you fill these in. They're in the back of the room next to the sign-in sheets, and you do 1 per course, not 1 per lecture, 1 per course. So you do 1 for relativity, 1 for electromagnetism, 1 for RF, 1 for longitudinal dynamics, and then we keep them at the end. And your feedback is definitely listened to, and we go through the feedback in detail at our education and training meetings at the end of each semester. So we have lectures every Monday. We take attendance every Monday. You have to sign in once per day, not once per lecture, not once per course, once per day. So every Monday you got to sign in. The sign-in sheet's in the back of the room. Lecture attendance is taken every 3 months and distributed to the supervisors, so they'll see if you're attending or not. So, and you've been told to sign in. So we had a problem with Liverpool students saying, "Oh, I just forgot to sign in." No. You've been told to sign in. That's not an excuse. We don't have attendance online yet. We're working towards that. If you have attended online, you watched it online but didn't attend in person, you could possibly email Ben and let him know, and you can add it to the sign-in sheet so we know you've at least watched it live. But it's attendance at all lectures compulsory to first years, and all the advanced lectures, all the second years have to attend. First years have to attend the advanced ones as well. If you have a special reason why you shouldn't be attending the course, you've got to let me know why. Otherwise, we've got to keep an eye on numbers. We have 50 students in Cockcroft. The advanced lectures should have 50 students here, but we don't, so we need to keep a track of why they're not attending. And if you're placed in our lab, you should follow on the webcasts. So just if you're going to spend your second year at CERN, you've still got to follow the courses online. And that's about it. It's just to give you it's a very brief lecture because I know it's lunchtime. Any questions? Or is it straightforward? Attend the lectures, do the exams. That's pretty much it. There's webcasts. If you see any students who aren't here who I don't quite realise yet these are compulsory, please let them know that they are compulsory. Attendance is taken and it is an exam. And hopefully we'll see more students next week. Okay, that's it then. Go have lunch.
Yeah, that's a small relativity. I'll give it another one. Currently, because everyone's doing one course a week, it's one to 2 weeks.